the antisymmetric requirement is satisfied. Now, if we just write down something without deep thinking, we would have written down something like that. Okay, so we will have 1s, one electron called labeled number 1 in 1s with an up spin, another labeled 2 in 1s with a down spin. I use alpha for 1, 0 column and beta for 0, 1 column as shorthand. Even one can use an arrow up, arrow down, okay? But last time we already illustrate the problem with this simple 2 electron wave function. It is wrong because if we interchange 1 and 2, that is the exchange symmetry we are talking about, or anti-symmetry requirement that we are talking about. If we interchange 1 and 2, we just write 1 into 2, 2 into 1, we get this one. Now we inspect whether this is related to this in some way. For example, it is off by a sign. No. Is it equal to the original one? No. That is to say, this particular one that we have in mind, 2 electrons in 1s, 1 up, 1 down, 1 up spin, 1 down spin, written in this way, does not satisfy our anti-symmetric requirement. In fact, it does not satisfy any symmetry requirement about interchanging 1 and 2. So I already stated the problem. What's wrong, number 1? In fact, because they are indistinguishable, we only know 1 is in up, 1 is in down, but we don't know which is which. But in this way, we are specifying a particular one to be up, the other one to be down, okay? So that is one error or one mistake that we have made. If we inspect closely, as I just pointed out, the one that we wrote down is neither antisymmetric nor symmetric. That is to say, the one that we wrote down does not have any symmetry property. But when we realize that, when we have a 2-particle wave function that does not have any symmetry property, that is not a problem for us because we can construct an antisymmetric form by forming this particular combination. So we wrote something wrong, no problem. If we do something like phi12 minus phi21 in our previous form, then it is guaranteed to be antisymmetric. Okay, I hope that you see it. If you switch 1, 2 in the first term, that becomes the second term in the previous form, and you switch 2, 1 in the second term, it becomes 1, 2, it becomes the former term. Therefore, with the minus sign in the middle, this will be antisymmetric. Okay, so we found a way out to write down something antisymmetric. Exploring this funny way deeper, we could also form a symmetric combination as well. Okay, that will be useful when we consider the excited state a bit later. Okay. So now let's step back a little bit. We are discussing helium ground state, no doubt. Okay, 1s, 1s. However, how about a more general situation that we can use it for discussing ground state as well as helium excited state later? Therefore, we are motivated to consider the situation where we have one electron, one particle in a state A, and other particle in a state B. Okay, so I just called it A, B, two different states. This A could include a description of spin. For example, it could be 1s up. The B could be 1s down. Okay, but A could be 1s up, B could be 2s up. Okay, so that A and B is a broader description of the state. It could describe everything about that particular state. Now, we have two particles in two states A and B. It is the same game. How to write down a legal wave function that satisfies the antisymmetric requirement, all right? That is what we are interested in. The physical picture is one particle in A, one particle in B. So that seems to make sense. But if we check interchanging 1 and 2, you will get phi A2, phi B1, okay? And that has nothing to do with this one. Okay, so it is neither symmetric nor antisymmetric. Again, we have seen a case in our ground state discussion. Well, you may think, how about particle number 2 in A, particle number 1 in B? So try this one again. You will see the same problem. Okay, but already we have hinted at a way to get out of this trouble. If we form phi A1, phi B2, plus minus phi A2, phi B1, we will have a symmetric form and an anti-symmetric form. Okay, so if they are electrons, two electrons, we have to compose something that is anti-symmetric. The anti-symmetric form has a minus sign in the combination. So at this point, it is the punchline. We have two electrons in two states, A and B. This particular way, equation 33A, is the anti-symmetric form of two electron wave function. Okay, so I pause here. At least, do you see this to be anti-symmetric? Is that okay? Okay. Now, actually in quantum mechanics, a good rule to keep in mind is that if you don't know anything, don't say it. Okay, now here is one realization. All we know, because the two electrons are indistinguishable, they are living in the helium atom, all I know is one electron in A, another electron in B. But in fact, I don't know which one is in which state. For this, we better don't enforce electron number 1 in A, electron number 2 in B. If we do that, we will get one of the terms, and then we are wrong. Okay? So we have to be fair. We don't know that, then we don't overstate it. Okay? So this is a fair way to write down what we know. Okay? And now, it is this minus sign that ensures anti-symmetric requirement. Mathematically, now the 1 over square root 2 is to keep the normalization, given that for the single electron state, 1s state, when we solve it, we have normalized the single electron wave function. So this is make sure, but it is not the most important point here, but that makes sure is that the whole thing, this one now is properly normalized. But let's focus on this combination with a minus sign. It can be written into a determinant. Okay, so I hope that at least you know 2 by 2 determinant, how to multiply it out. It is not a matrix, okay, because a determinant is a symbol that you need to do diagonal one multiply minus the off diagonal terms multiplied to each other. So this is this one, okay? But writing something into this determinant form is very suggestive. It is telling us something about what to do when we have 3 electrons, 4 electrons, or 8 electrons, or any number of electrons living in the vicinity of each other. Writing it as a determinant also have a lot of advantages because we can make use of simple determinant mathematics. For example, if we have 3 electrons in 3 different states A, B, C, if we follow this idea, we could write down a 3 electron wave function that is guaranteed to be antisymmetric. There are actually 6 terms here. You have, with each term having 1 electron in A, 1 electron in B, 1 electron in C, but the 6th term refers to all the possible division of particle 1, 2, 3 into A, B, C, plus a proper assignment of the +1 and -1 sign in front of each term to ensure that the whole 3 electron wave function is antisymmetric. Now, if you do it on one single line, in principle, we know what to do, right? Just make sure that we have all the possibilities accounted for, then play with the sign in front of each of the 6 terms, make sure that when you interchange 1 to 2, 2 or 3, 1 or 3, okay? Every time you do this, you have a minus sign, okay? Now that can be troublesome when you have 4 electrons, 8 electrons, things like that. But if you use the determinant form, life becomes much easier, you see? Now, if you write it down, when you interchange 1 and 2, so you interchange the label, the variable of electron number 2 with electron 1. Last time we draw a picture, okay, 1 electron is in this location, the other is in that location. You switch them, that is the same physical situation. So in the determinant form, we are switching the label. We replace 1 by 2, 2 by 1, okay? But there is a very interesting determinant mathematics result. When you interchange 2 columns or 2 rows of a determinant, there is always a minus sign. Okay, I hope that you know this fact. Okay, now if not, go back to your mathematics book. Okay, I think in year 2, then you just 1 or 2 pages of reading will refresh your memory. Okay, so in this form, it is guaranteed to work. So let me introduce the name for this kind of way of writing the many electron wave function in terms of single electron states. Okay, now that is the way to implement the antisymmetric requirement when we have solved the single electron states. This may be 1s up, 1s down, 2s up, for example, lithium, ground state. Okay, that is the way to write it out. Okay, now the name of this kind of form is called Slater determinant. That is after a physicist, Slater, who has contributed much to the understanding of atoms, molecules, and solids using quantum mechanics. He was also the chairman of the MIT physics department, I think right after the Second World War. And from that time on, he brought up the whole department to the reputation that it is enjoying now. And I think he was a student of Wigner, Eugene Wigner, who won a Nobel Prize for using group theory in quantum mechanics. So now we can handle any number of electrons in the same number of single electron orbitals. Okay, now we have left out another possibility, the plus one, okay, the plus combination, because we are looking for the antisymmetric one. I just want to mention that if you use this, you will get a symmetric one. Okay, but if you think back to our ground state problem, okay, now for this one, if we have two particles but in the same state when A equals B, okay, then we don't need to do this. In fact, we can write it down like this. This is also symmetric. All right. Now, but that must be wrong for two electrons. If you say A is 1s up, A is 1s up, this is illegal. You know it from high school. If we rotate or transform using rotational matrix or other, I don't think so. I don't think so. Okay. Now notice that they are not numbers. They are functions inside the determinant. Okay. It is a shorthand or a very convenient way to make sure that when you distribute n electrons into n states, you have accounted for all the possible ways of distributing n electrons, each in each state. Okay? Now, this page is just a remark. We are looking for the antisymmetric one, okay? But later on, we will see that knowing how to write a symmetric combination will also be useful in the discussion of helium atom excited state. Now, punchline number 2, okay? Number 1 is the determinant. Number 2 here. Now, we can obtain the Pauli exclusion principle as you learned it before. So when we start off with 2 electrons in 2 different states, we have written down this Slater determinant form. All right. Now, what if state A and state B are identical? All right, let's see what's wrong with it. When B is the same of A, we will have this 2 electron wave function become identically 0. And this identically zero applies to all coordinates of 1 and 2. That is to say, simply put, you have written a lousy thing called phi equals 0. Nowhere you can find your 2 electrons. That is to say, you have written down something nonsense. Follow me? Okay? 得唔得？行不行？ Okay? 2 points here. 2 points here. It is 0, but it is 0 for every location of 1 and 2. That is to say you have destroyed your particles. Okay? You are writing down something that the 2 electrons are not there. Okay? So this is unphysical. Therefore, don't allow this to be the case. Okay? So let me summarize. For 2 electrons in 2 states written down in the legal antisymmetric form as the determinant, state A and state B cannot be the same. Okay? Get this point? Okay? Now, switch the statement a little bit, but the same meaning. You cannot put 2 electrons into the same state. But now, in this statement, conceptually, we have already making use of single particle states, the phi A and phi B. That is already an approximation behind this statement, because 2 electron wave function in general cannot be decomposed into single electron states, product of single electron states. Here, we make the approximation, we relied on this Hartree Fock self-consistent calculation. In our mind, we do have 1s, we do have 2s, 2p, etc., so that we can write down a determinant. We know how to write something down that obeys the antisymmetric requirement, and from that, we realize one additional principle, okay? So I will downgrade it to Pauli exclusion rule, okay? Because that is a consequence of the antisymmetric requirement. That is a higher rule, higher principle. So now we understand that Pauli exclusion principle is a byproduct or a consequence of the more general statement that you must have antisymmetric many electron wave function. Okay, so follow my logic. Okay, is that okay? Now that is the moment that you upgraded your knowledge. You have learned the Pauli exclusion principle, memorize it in chemistry course, okay? But now you understand at a higher level of understanding, it is not about single electron states. It is about the antisymmetric requirement of many electron wave functions in general. Okay, so do you get my conceptual point? Is that okay? Understand? Okay, now learning is about upgrading your knowledge, right? If you always fall back to what you learned in high school, then it doesn't mean anything. Can we obtain the form of antisymmetry by perturbation, first order correction of the wave function? It is a different class of questions, okay? Perturbation means we have a part of the Hamiltonian that we know how to solve exactly. Then there is an additional term we don't know how to do. Then we will do perturbation. Do you understand the problem? Okay. So now, for example, you have this n electron system, helium ground state. You can write it down. Now, if you shine in a light, something else, in your Hamiltonian, there will be an additional term. Do you follow me? Okay. And then you may want to use a legal ground state you written down, and then try to use perturbation to study the effect of what happened when a beam of light incident upon a helium atom. Okay, do you understand what I'm saying? Okay. It is a different class of problem, I would say. So now it's time to get back to the helium ground state. Okay. The previous page is about A, B, general. So now get back to helium ground state. You can think about this A and B state as one as up, one as down. Okay, or one as alpha, one as beta, down. Okay, no, this one is about same state, and that is violating. We know that is zero, entirely zero, okay? But this one, okay? So now we have one as up, one as down. Therefore, we just plug it into our slated determinant, then we will have A and B. Now notice that they are not the same. The fourth quantum number, so-called by Pauli, they are different. Okay. Now, if you multiply this out, it will be something like that. All right. Then what is this? This is, sorry, this is 1s up. Okay, this is 1s down. So the term that we multiply together there, let me see. Okay, so this is exactly the wrong thing that we constructed at the beginning, but now if we linear combine with another wrong term, but with the coordinate switch, that is guaranteed to be antisymmetric. That is okay. Okay, so now we will look at this final form a bit more when we go to the spin property of the ground state. We will notice that this is a spin singlet state, S equals 0 state. We will see that a bit later. So we have Pauli exclusion principle demonstrated for the 2 electron case. You may wonder, is it general? Now, again, I use the 3 electron situation. We know how to write it down in 3 different states, A, B, C. Now you can play the game again. If any state, A equals B, or A equals C, or B equals C, any 2 of the 3 states happen to be identical, you have 2 identical columns or rows. By determinant mathematics, it is identical 0 for all the coordinates value of 1, 2, 3. Thereby, you have the same nonsense. The particles have disappeared, vanished. So you don't allow that to happen. That means all the states must be different. You switch the idea of the statement, then you cannot put 2 particles into the same state, any same state. Okay, that is the Pauli exclusion principle. Of course, you can generalize it to n electrons in n different states, okay? And then you will realize that when the states, two of them becomes identical, or suddenly everything becomes zero. So that is a idea behind how to realize anti-symmetric requirement in terms of single particle states in a determinant form. Okay, and that is an important starting point for those of you who want to move on to fancier topics such as a big branch called many body problems. At least you know how to write down a legal many body wave functions. And it is also interesting to compare the difference in the physics between fermions and bosons. Last time, I mentioned that nature made both options, meaning nature make use of the symmetric option for n-particle problems, as well as the anti-symmetric option for many body problems. Only that one class of particles called fermions, including electrons, they make use of the anti-symmetric option. There's another class of particles called bosons. They make use of the symmetric option. Are they behaving very differently? That is the question I want to have a very brief discussion here. It is easier to see the difference about ground states. For example, I have many electrons or many fermions particle in a box. Okay, so easy. Particle in a box, you know how to solve all these states, right? You have infinite many states. Those are the horizontal lines that I draw here. Now, given that you have 10 fermions, 10 electrons, for example, even they are not interacting, they are not Coulomb repelling, okay, but they obey Pauli exclusion principle because they are fermions, because they have to obey anti-symmetric wave function. This very fact, even for the ground state of these 10 fermions, they have to step up in energy because Pauli says you cannot put another one in either upspin or downspin. And we saw the origin of that has to do with the anti-symmetric wave function requirement. Okay? So now do you understand that in fermions, even in zero temperature, ground state means zero temperature, right? They have to step up in energy. Okay, do you follow this? Is that okay? Following? Understanding? That is to contrast with boson's case. Boson's symmetric wave function, there will be no Pauli exclusion rule. You don't have the determinant representing it in single particle states, okay? So one single particle state, you can put all the bosons into it. So if you are looking for the ground state, then it is easy to see. Just put all the 10 bosons into the lowest single particle state, that is the ground state. Okay? Now you see the energy, ground state energy of this whole system is very different from the ground state energy of the fermion system. Do you see that? Okay. Now, for those of you who are taking, who are you doing this course? Yeah, okay. So for those of you who are doing the thermal and statistical physics this semester, you will soon see that the fermions obey so-called one kind of distribution called Fermi-Dirac distribution, and the boson follow another type of distribution called Bose-Einstein distribution. But here you don't need this knowledge. Ground state, you just look for the lowest energy way, right, to fill in the fermions and bosons. And that difference is a very big piece of physics. And I think it's related to our being, okay, why we are here talking physics. For example, in astrophysics, you have learned, you have heard, well, some of you have heard, there is something called the degenerate pressure of a Fermi gas. A Fermi gas means a collection of fermions. They do not interact, but they obey Pauli exclusion principle. So as I already illustrate, you can think about n fermions in a box. The box is L by L by L, cubic box. So everybody knows how to solve this particle in a box problem. So the allowed states will be in this energy. Then you fill in all these fermions up, because Pauli exclusion principle, after this is occupied, you have to go up, and then you run out of fermions. This will be called the Fermi energy. If you haven't heard about the Fermi energy, don't worry, I don't need it here, okay? But that is the meaning of the Fermi energy. Now, think about that if the box becomes a little bit smaller. So this is smaller than the previous one. The volume is squeezed a little bit. Because of the particle in the box solution has the length in the bottom, in the denominator, when L becomes smaller, the states becomes spreading separate, farther apart, okay? So here I draw this spacing being bigger than this side because the box is smaller. But you have the same number of fermions, therefore you fill it in. Energy-wise, you will get a higher energy because the single particle states becomes spread farther, okay? Now, you have the scenario. You have a volume V, you have an energy, you have a smaller volume, you have a higher energy. Then in thermophysics, you call this change in energy due to a smaller volume, decreasing in volume, the pressure. U is, there's a term called minus PdV, right? In your first law, second law, right? So TDS is, TDS is du minus, du is TDS minus PdV, okay? Have you seen this, I think? Hello, hello. Okay, so now when you see this, that means the fermion in the box, when you try to squeeze the box, the fermions is exerting a counter force, okay? And that is expressed here as the pressure due to the fermions in the box, okay? They try to oppose any contraction of the box. In astrophysics, gravity wants to pull some dying star, collapse them, but when you have electrons in your dying star, then because electron has a light, well, it's the lightest particle in your standard model, and the mass appear down here. So the degenerate pressure exerted by the electrons in a dying star would give you a pressure to oppose the gravitational pull, okay? And sometimes it can balance it for a long time, millions of years, you see that, or staying there, okay? Of course, maybe gradually gravity wins, okay? And then something will happen again. The density will become very high. Electrons will be captured into the nucleus called electron capture process. Then you generate a lot more neutron. Therefore, sometimes you get a neutron star, okay? And at that point, neutron is a fermion, it's particle in a box again. Neutron could also exert a Fermi, this degenerate pressure, okay? So this is a very simple idea. You can easily get when you understand Pauli exclusion principle. That is the rule that stems from the antisymmetric requirement of fermions, and that will give the pressure opposing squeezing of a box. Okay, so that this effect, if you play with bosons, it doesn't work. Okay, the boson will stay always stay in the ground state. Okay, so you see the difference there. Okay, and I think we relied on this effect to become what we are, right? We have gold. We have the heavier element that is understood to be the result of some supernova event. So here we ended the discussion about how to write down the helium ground state. We know what to do now, okay? So after the break, we will look into the form of the helium ground state wave function. In particular, we will see that for helium, 2-electron situation, there is a very interesting separation of a spatial part, the 1s orbital part, and the spin part. Such separation may not work for 3 electron, 4 electron, more electron, but for 2 electrons, that works. And in the spin part, we realize that that is a very funny combination of 2 electron, 1 up, 1 down. Again, that reflects our ignorance. We only know that 1 up, 1 down. We don't know which one is up, which one is down. In fact, we can't know which one is up, which one is down, because if we do, the wave function does not follow the rule, okay? We found that the spin part is up, down, and down, up linear combination. And that may be the first form that you see as an entangled state. 2 particles with this, in this wave function. If you later on make a measurement, for example, you found this one is up, the other one must be down because they are born this way. Okay, so we will discuss a bit about this ground state wave function, the spin part, and then that will motivate us to look at the excited state of helium atom, and then some wonderful physics about why we have magnetism will come out, okay? Some deep and very important concepts, although the system is very simple. It's just helium, okay? So a break now. We will resume in 5 minutes or so, okay?